I must say that I'm going to borrow that saying that you have, fools with tools are still fools. So it is my pleasure to introduce to you our final speaker before lunch, Dr. J.P. Guéroux. Dr. Guéroux, Chevalier in the Order of the Légion d'Honneur and a former professor of geotechnical engineering. He is now a consulting engineer. He's a member of the United States National Academy of Engineering. He has a doctor honoris causa of the Technical University of Bucharest. He is past president of the International Geosynthetic Society and chairman emeritus and founder of Geosyntec Consultants and chairman of the editorial board of Geosynthetics International. He will be talking today about the use of geomembranes for lining canals. So it is my pleasure to introduce to you Dr. Guéroux.
Thank you very much for this kind introduction, and thank you for inviting me to speak today on behalf of the IGS, the International Geosynthetic Society, which was founded 35 years ago and has 4,000 members in 100 countries. And it is a very active society which has already organized 11 international conferences. I apologize for speaking from the floor, but considering the nature of my presentation, this will be far more efficient. So we are going to talk about the use of geomembranes for lining canals. Geomembranes are flexible sheets of watertight material, generally polymeric, but sometimes bituminous. Geomembrane panels are seamed together to form large geomembrane liners, which are used in a variety of applications, such as waste disposal, landfills, reservoirs, embankment dams, concrete dams, and today geomembranes are used in a variety of canals, hydroelectric canals, navigation canals, irrigation canals, large canals, as well as small canals. The geomembrane can be exposed or can be protected. The use of geomembranes in canals started in the 50s with asphalt sprayed on jute and mostly films of PVC and polyethylene, very thin, typically 0.2 millimeter thick. Here is a historic photo of the first canal lined with a PVC film in 1954 in the United States. But in spite of this long history of geomembranes used in canals, and in spite of the fact that geomembranes are today the dominant waterproofing materials in waste disposal landfills and in mining applications, many canals are still lined with concrete. There are two types of concrete linings: precast panels, which are often used in small canals and placed by hand, and cast in situ concrete linings, which are often used in large canals and placed by big paving machines. But they can also be used in medium-sized canals, as we see here. There is considerable experience with concrete linings, but concrete linings have drawbacks. Cast in situ concrete linings are not flexible. If they are not uniformly supported by the soil because of causes that all geotechnical engineers know: differential settlement, low guidance, dissolution of gypsum in collapse, burst, or erosion of soil under the lining. And here we see a longitudinal crack in a concrete lining. This is another example of cracking of cast concrete lining. And there had been in an unsuccessful sealing the crack with tape. This canal is located in an area where the soil has a high content of gypsum. This happens in particular in desert areas, as in the Middle East in many cases. And gypsum is soluble in water, which explains the mechanism of the failure of this cast in situ concrete lining. Water leaking through initial cracks of the concrete lining dissolved some gypsum, which caused soil settlement, which increased the concrete cracking, thereby increasing leakage, which caused more gypsum dissolution, which caused more settlement, which further opened cracks and joints in the concrete lining, and so on, until the canal was put out of commission. So there are cases where the dissolution of large amounts of gypsum by water leaking from the canal causes the formation of large cavities in the ground. This is another example in the Middle East, where the concrete lining collapsed into a cavity formed by a gypsum dissolution. As seen in these examples, water leaking through cracks in the concrete lining can cause a major failure if the soil is sensitive to water. Now, the gypsum case that I presented in the preceding slides is frequent in desert areas, as in the Middle East, but is relatively rare worldwide. But there is a frequent case where the mechanism is similar. This is the case where water leaking through initial cracks of the concrete lining erodes the soil under the concrete lining. As a result of erosion of the soil, the concrete lining is no longer uniformly supported, which causes cracking of cast in situ concrete lining and cause differential displacement of precast concrete panels, which we can see on the next slide here, a case of differential displacement affecting concrete panels. The displacement of concrete panels occurs also in the case of frost heave. In the case of freezing temperature, water vapor present in the soil migrates toward the cold lining, and as a result, ice accumulates under the concrete lining, forming ice lances which uplift the concrete panels. This is an example of frost heave affecting precast concrete panels. And in addition to frost heave, there is another deterioration mechanism due to frost. Concrete is a porous material, therefore concrete linings contain water, and in case of freezing temperature, when water is turned into ice, its volume increases, which progressively breaks the concrete after some freeze-thaw cycles. This is an example of concrete deteriorated by frost. Now, it should not be concluded from the preceding slides that all concrete linings have problems. There are many canals where concrete lining is performing well. However, the preceding slide shows that there are several mechanisms that can deteriorate concrete lining. Therefore, a number of canal linings have been repaired and need to be repaired, and there are many examples of defective concrete-lined canals that have been repaired using geomembranes. Now, it should be noted that many geomembrane linings having an excellent performance are protected with a concrete layer. So a good way to use concrete in canals is as a protective layer of the geomembrane lining. The geomembrane ensures the water tightness, and the concrete ensures the protection of the geomembrane. This leads us to discussing water tightness. The evaluation of water losses in canals, and in fact, therefore, the evaluation of water tightness of lining materials is a major subject of discussion in irrigation canals. Two methods are used to measure water losses: the inflow-outflow method and the ponding test method. The unit typically used to express water losses in canals is millimeter per day, which is a unit of water level drop. The inflow-outflow method consists in comparing the flow rate at a certain point along the canal with the flow rate at another point located downstream, and the difference is the water loss between the 2 points. This method lacks sensitivity and cannot measure water losses less than 10 millimeters per day. The ponding test method consists in creating a pond by using two cofferdams to separate from the rest of the canal a canal section of about 300 meters long and measuring the water level in that pond during several days. This method is more sensitive than the inflow-outflow method. However, it cannot measure water losses lower than 3 to 5 millimeters per day. So let's see now a summary of water losses in canals for typical depths of water of 3 meters. First, in the case of an unlined canal, no geomembrane, no concrete, on a silty to sandy soil, we have a loss of 100 to 1,000 millimeters per day. And canal designers often use a typical value of 250 millimeters per day for unlined canals in silty to sandy soil. Concrete lining in good condition, 25 to 50 millimeters per day. Concrete lining in poor condition, more than 100 millimeters per day. Geomembrane well installed, less than 1 millimeter per day. The geomembrane poorly installed, between 1 and 10 millimeters per day. And of course, a geomembrane with very large holes can be anything like more than 100 millimeters per day or more. So comparing these values presented in the slide with the sensitivity limit of the two methods shows that both the inflow-outflow method and the ponding test method cannot evaluate geomembrane lining in good working conditions. This method could only detect a seriously damaged geomembrane. Here is an important comment. Based on the result presented, it appears that a concrete lining in poor condition, and we have seen some examples, may leak as much as an unlined soil. And this is not surprising because leakage analysis shows that even relatively thin cracks in a concrete lining could result in significant leakage rate. Now, let's review a few case histories of canals lined with geomembranes. Let's start with the first example of modern canal design. So we are no longer in the 50s, but in the 70s. This case was in 75 at the design stage. And it was in the Middle East in the 70s. There had been several failures of canals lined with concrete and canals lined with plastic films. Remember, plastic films very thin, like a 0.2 millimeter thick. Therefore, 1975 was the right time to consider that geomembranes, which are thicker and stronger than plastic films, could be used for lining canals in the Middle East. This project was the Isfahan Canal in Iran and constructed 76 to 79. It was the first large irrigation canal lined with a geomembrane. It was 4 meters deep, 15 meters wide, and 50 kilometers long. The existing concrete lining was constructed in the early 70s, but it had deteriorated rapidly due to the dissolution of gypsum present in the ground, according to the mechanism that we have described earlier in this presentation. So as a result, the existing concrete lining was severely cracked 5 years only after construction. So the canal had to be relined, and the geomembrane on choice at that time was butyl rubber geomembrane. So the specifications from the canal designer called for a leakage rate less than 1 millimeter per day. We know from one of the preceding slides that this can be easily achieved with a geomembrane, but it cannot be verified by a method for measuring water losses. The challenge was to meet this goal with a geomembrane placed on concrete with cracks that could evolve with time, and concrete where new cracks could even appear in the future. So it was a new challenge at that time. An extensive theoretical study was conducted, and a study showed that placing an independent geotextile next to the geomembrane, between the geomembrane and the existing concrete, would significantly reduce the tensile stress in the geomembrane in case of crack opening in the future. So the following configuration was adopted. At the bottom is the existing concrete. It is overlain by the geomembrane between two layers of geotextile, and the new concrete protection placed on the top. What is the role of the geotextile above the geomembrane? It protects the geomembrane, in particular during the placement of the concrete protection. It reinforces the concrete during placement on slope, because fresh concrete can be unstable on a slope, and it drains the excess water from fresh concrete, which also contributes to the stability. What is the role of the geotextile below the geomembrane? It protects the geomembrane from puncturing by sharp edges of the underlying concrete, because we know it is badly cracked. It is also a low friction interlayer that decreases stress in the geomembrane if and when a crack opens in the future, and it will support the geomembrane to prevent the geomembrane from bursting under water pressure while bridging cracks in the existing concrete lining. So the geotextile plays a very important role. We see here the geomembrane being unrolled on top of the geotextile. The panels were prefabricated in factory from rolls about 2 meters wide, so they were assembled together to form panels 16 meters by 15 meters. 2 panels were installed every day. We see here a historic welding machine for butyl rubber geomembrane. I should immediately reassure you, modern welding machines are much smaller and far more sophisticated. This is a general view during installation. The geomembrane was protected by concrete, unreinforced at the bottom. Initially, the concrete was reinforced on the slope, but some full-scale tests in the field showed that unreinforced concrete was stable when it was cast on the geotextile, whereas a test showed that casting the concrete directly on the geomembrane was unstable. This is because the friction angle between concrete and butyl rubber is relatively low. And the stability was ensured by the geotextile for 2 reasons. It reinforces the concrete, and perhaps more importantly, it drained the excess water from the fresh concrete during placement of the concrete. Therefore, unreinforced concrete was finally used in this canal, as we see here. This canal is still in service more than 40 years after being lined with this butyl rubber geomembrane. Today, we don't use butyl rubber anymore because it has been replaced by another elastomer, EPDM, which is even more durable. So 40 years was already very good, but we can do even much better today. Here are examples of the use of EPDM geomembrane in a concrete-lined canal that needed to be repaired. Now, almost 40 years after the Esfahan Canal, the designers of the Tecapo Canal, a large hydroelectric canal in New Zealand, faced a similar challenge: how to ensure that the geomembrane could resist a crack. In that case, there would be crack created by a seismic activity. So an extensive design effort was undertaken, and the seismic analysis showed that a possible range of cracks with a width of 30 to 80 millimeters. The first screening of geomembrane candidates resulted in the pre-selection of 2 geomembranes, an HDPE geomembrane and a composite geomembrane. The composite geomembrane is described here. It comprises 2 layers, a PVC geomembrane that has been thermally bonded in the factory with a non-woven geotextile. Here are the results of the analysis of the stress induced in the geomembrane by the opening of the crack. The results are ranges, a factor of safety because of the variety of the cases considered. And the results show that the factor of safety in this case was higher than 2 for the PVC composite geomembrane and could be less than 1 with the other geomembrane. So the conclusion of the analysis was that the composite geomembrane was selected, even though the cost of the high-density polyethylene geomembrane was lower. And this is important because it's important to note that for this project, the geomembrane type was selected as a result of a rigorous technical analysis. This comment is important because in too many cases with geomembranes, the geomembrane type is selected based on cost. Or even worse, it is selected based on the experience of the design engineer with a certain type of geomembrane, but in a completely different application, often waste disposal landfills. Geomembranes are routinely used in waste disposal landfills, but the experience gained there is not applicable to canals. An important aspect of this project was the design of the ballast on top of the geomembrane. Ballasting and anchoring geomembranes is needed against the drag forces and uplift forces exerted by water. The drag forces tend to displace the geomembrane in a flow direction. However, these forces are not very effective if the geomembrane is in contact with the underlying medium, because calculation shows that the interface friction forces beneath the geomembrane are always higher than the drag forces above the geomembrane. So as long as the geomembrane is in contact with the bottom of the canal, the drag forces do not displace the geomembrane. But if the geomembrane is uplifted, it is no longer in contact with the bottom and the sides of the canal. And as a result, the drag forces are no longer counteracted by friction beneath the geomembrane, and the geomembrane is carried downstream unless it is properly anchored or ballasted. This photo illustrates the importance of anchorage. We see here on the right an anchorage beam. And in this canal, the geomembrane left of the